Hey guys, welcome to lecture number 21. In this lecture, we will start something new. We will deal with integration. There will be 5 lectures here. And in this first lecture, we'd like to talk about anti-differentiation, and you will see a bunch of techniques of how to compute indefinite integrals, first of all. So let's get started. First, I would like to say a few words about how is this related to differentiation, and I would like you to see the difference between the two. Okay, let's get started. So first we'll talk about anti-differentiation. Okay. So first of all, what is an antiderivative? So an antiderivative like to see what this is. So the antiderivative is nothing else. So a function f, and we denote this by capital F, is called an antiderivative, and let's so antiderivative of a given function f, say f, on an interval I, right? If this thing, if f prime, capital F prime of x is f of x. So that's what we call an antiderivative. And this happens for all x so for all x in the interval I. So that's what we call an antiderivative. And now let's see some examples. And in these examples, we will show derivatives and antiderivatives. So let's draw the, let's write it like this. So here we have derivative. And here we will have antiderivative. In fact, we don't need this. So, okay. So keep in mind that we have this definition, right? So that's what you need to know, that capital F prime of x is nothing else than just f of x, all right? And now, let's see. So you know from the derivative that, for example, let's use Leibniz notation, that the derivative of x cubed with respect to x, this is nothing else than 3x squared. So we know this, right, already. So now we will let f prime, capital F prime of x to be 3x squared, right? And well, we will say that antiderivative of 3x squared means what is 3x squared derivative of? So let's write this. So antiderivative of 3x squared means, and I'm going to write this question like this: what is 3x squared the derivative of? Right? And now the answer, well, 3x squared is the derivative of x cubed. Or you can say x cubed plus another constant, 5. Or you can say x cubed minus 10, or x cubed plus pi to the 4th, and so on. You see, so you can add a constant here, so it doesn't really matter. And in the same way, we can say that the derivative with respect to x of x cubed plus 5 is the same as 3x squared, right? Because here you apply the sum rule, right? And you'll have that this is the derivative of x cubed with respect to x plus the derivative of 5 with respect to x, which is 0, right? Because it's just a constant. And in the same way, we can say that the derivative of x cubed minus 10 is 3x squared, or we can say that the derivative of x cubed plus pi to the 4th is 3x squared, and so on. So in general, we can say that the derivative with respect to x of x cubed plus a constant is nothing else than just 3x squared, where c is any constant. And here we can say the same thing in general. We can say that 3x squared is the derivative of x cubed plus a constant, right? So see, constant is a constant. And we can say that the antiderivative of 3x squared is x cubed plus constant c, right? So that's so you can say that is the operation which is in a way the inverse of the derivative, if you want to say it like this. All right, and I think you got the idea. We'll do more application, and you will see exactly what do we mean by that. But first, I'd like to draw your attention with the following theorem. So Theorem One, and this theorem will concern the antiderivatives of a function differ by a constant. That's what we're. So anyway, the antiderivative of a function. Well, I said it, the antiderivatives will differ by a constant, so we will say that if capital F of f is an antiderivative right, of the continuous function f, then any other antiderivative let's say g, right, capital G, of f of the same function has the form and I'm going to write it like this: g of x will be nothing else than f of x plus that constant. So in other words, antiderivatives of a function differ by a constant. That's what we need to know, right? So in other words, two of antiderivatives of the same function will differ by a constant. And now let's point out some notation. So notation is the following. So for the antiderivative is that this integral of f of x dx, so as you can see here, we'll write it in this way, will be capital F of x plus this constant. And here, C is a constant. C is a constant, right? Capital F is the antiderivative of F. And we will call this, and now we will call this the indefinite integral of F. So this guy, so we call this guy here the integral of f of x dx, the indefinite integral so this will be the indefinite integral of the function f. So that's what you need to know, right? This notation, $, whatever you want to call it. All right, and also it's clear that it will satisfy the condition. So clearly, since f prime, capital F prime of x will be nothing else than just f of x. So that's what we need to know. Let me box this because it's very important for you to know it. So when you compute the integral of a function, you'll get another function which will be the antiderivative of the function under the integral. So that's what you need to know. All right. Now let's see some examples. I would like to go back to the previous example since we talked about the derivative of x cubed. Now I would like to compute the integral. So we have that the integral of 3x squared dx will be nothing else than just x cubed plus a constant, right? So this is what we call, this guy here. So this, we'll call this the indefinite integral of 3x squared. So that's what you need to know. And now let me draw a picture so that you can see it clearly. In fact, let me write with the red again. So the way we're going to do is the following. So I'm going to, so here I have, let's say f of x is, in fact, no, let me. So here I have f of x is 3x squared, right? And here, let's just say I have capital F of x is x cubed plus a constant, right? So when I go from here to here, I can go from here to here. So here is the antiderivative, which is the integral of f of x dx. And this will be capital F of x plus a constant. And from here, from capital F to here, we will have the derivative, which will be nothing else than just, so we'll have that f prime of x is f of x, right? Okay, so that's the picture you should have in mind. All right. Now, we can say that the graph of f of x plus c for different values of c is called a family of functions, right? So keep that in mind. So it's we can say a family of constants. All right. Now, if you look at my notes, and in fact, you will find the basic integration rules. And I would like to mention just a few of them. So some procedural rules, how to add, how to subtract integrals, how to multiply by a constant, and so on. And then at some point, I will also mention a couple of them. So let's talk about the differentiation formulas and integration formulas. So let me mention here. So differentiation. Formulas. Okay. And here we will mention integration formulas. Okay. All right. Let's see. So the first one I would like to mention is the constant multiple rule. And in fact, I will have the following. So d over d of c times f, right? So this is nothing else than just c times df over du. So this is what we call the constant multiple rule. And for the integration, we will have something like, if we integrate this function, c times f of u du, this will be we'll take the constant out, so this will be nothing else than c times the integral of f of u du. Okay, that's great. So this is the constant multiple rule for both of them. Now, okay, let me write it here as well so that it's clear. Constant multiple rule. All right, now the second one will be the sum rule. So when you have something like d over du of, let's say, f plus g, this will be df over du plus dg over du. And here you will have that the integral from f of u plus g of u du is the integral of f of u du plus the integral of g of u du. And we call this the sum rule. And the same goes for the integral. All right, that's great. Now, we would like to also the same thing works for the difference. Well, the difference is actually the sum, but anyway, let's write it. So we will have that d or du of f minus g is df over du minus dg over du. And the same goes for the integral. So it's the integral of f of u minus g of u du is the same as the integral of f of u du minus the integral of g of u du. And we will call this the difference rule. Okay, and now one more thing. Also, we can put together, since the first one and the second one and the third one, if you want, and we can have the linearity rule. Well, if we put all three together, we can have something like this: d over du of f. Let's say, well, let me put it like this: alpha f plus beta g is alpha times df over du plus beta times dg over du. Of course, alpha and beta are just constants. Let me mention here, are constants. And the same goes for the integral. So for the integral of, I should have written this in red anyway. Let's do it now. Oops, sorry about that. So d over du of alpha f plus beta g is is equal to, alpha df du plus beta dg du, and the same goes for the integral. So the integral of alpha f of u plus beta g of u du, this will be equal to alpha times the integral of f of u du plus beta times the integral of g of u du. And we will call this the linearity rule. Okay, so this sums up the rules for the integrals. So I want you to look at them. These are the rules. So the constant multiple rule, the sum rule, the difference rule, and the linearity rule. In fact, the only thing you need to remember is the last one, because the last one will include all the others. Okay, now I'd like to mention, and I hope you will go back and look in the notes, because in the notes you will see exactly how to find the antiderivative of elementary functions. But in fact, let me just mention a couple of them, and then so basic rule for differentiation and integrals. Okay, all right. The first one is the constant rule. Again. And what we do here is, okay, let me write it like this. D over dx, right, of a constant c will always be 0. But now with the integral of 0 du will be 0 plus constant. Okay, now another one is the exponential rule. Which says the following. Well, you know that the derivative of the exponential, let's just say d over du of e to the power u. By the way, this u is a function of x, right? This is, no, actually, let's keep it like this. It's u, so it's e to the power u, right? And for the integral of e to the power u du is nothing else e of u plus constant. Because we haven't learned the change of variables yet, so I don't want to go into detail. So imagine EU is just like x, for example. Is not a function of x. Otherwise, we have to deal with some kind of a u substitution and so on, and we haven't learned that yet. So we will deal with that in the next lecture, next or the third lecture in this chapter. All right, so this is the exponential rule. On the other, we can have also the power rule. And the power rule will be something like this. So if we differentiate of u to the power n, this is nothing else, n times u to the power n minus 1. So we know this already. But now if we want to integrate u to the power n du, so we have to look for a function such that differentiated, it will give me u to the power n. And that function will be what? Well, we have to be careful here, and I'm going to put it like this. For example, if n is different than -1, we will have that this is u to the power n plus 1 over n plus 1. plus c. So if n is not -1, right? And if n is -1, we will have this is natural log of absolute value of u plus constant plus c if n is -1. So you have to keep this in mind. Okay, let's separate these two. All right, and now the fourth one for both of them, so let's say logarithmic rule. So the logarithmic rule is the following. So we have d over du of the natural log of the absolute value of u. This will be 1 over u, as you know. In fact, let me write it with red. So d over du of the natural log of absolute value of u, right? This will be nothing else than just 1 over u. But now if we want to integrate, it is included in the above rule, right? As you can see. So included here. Right? Okay. Let's see, what else do we have? The fifth one, logarithmic rule. And also we will have some trigonometric rules. So I'll just mention sine and cosine, and then I'll leave it, the rest to you to read them from the notes. So trigonometric rules. But the same scenario works for the others as well. So here we'll have two of them. And what I will mention the following. So like I said, I will mention sine and cosine. So you will have that the derivative of sine of u is cosine of u, and the derivative of cosine of u is negative sine of u. And now for the integrals, so you'll have the integral of sine of u du is negative cosine of u plus c, and the integral of cosine of u du is nothing else than just sine of u plus the constant c. Okay. So that's what you need to know. And like I said, for inverse trigonometric functions and for the other trigonometric functions such as tangent, cotangent, secant, cosecant, you can look them up in the notes. All right, now let's do some examples. We would like to do as many examples as possible. Examples. The first one that I have in mind is the following. So let me just take the function f of x is x to the power 5, so x to the 5th. It's very simple, so I would like to compute the antiderivative of this, or the integral. So we'll have that the integral of f of x dx will be the integral of x to the 5th times dx. And now if you look at the power rule, this will be x to the power 5 plus 1 over 5 plus 1 plus c. So here we apply the power rule. And this will be nothing else than just x to the power 6 over 6 plus our constant c. So c is an arbitrary constant. C is an arbitrary constant. Okay. All right. Now, let's see another example. Let's just say, so the second one, let me see. All right, now, So just like I said, we have that by using the power rule, we will have that the integral of x to the fifth dx is nothing else than x to the power 6 over 6 plus c. All right, now let's see a second example. Now let's just take f of x to be 1 over x. Okay. So now in this case, the integral of f of x dx, which is nothing else than the integral of 1 over x dx, will be equal to, so this is x, let's write it in this way, x to the power -1. But this time this will be the natural log of the absolute value of x plus c, where again c is an arbitrary constant. All right, so now in this case we apply the power rule for n equals -1. Now let's see another quick example. Let's just say we have f of x is sine of x. Again, the integral of f of x dx will be the integral of sine of x dx, which will be negative cosine of x plus c. Again, c is constant, is an arbitrary constant, right? So we have this. Anyway, now let's see another example. Let's just say we have the fourth one, f of x to be 5x cubed. So in this case, we have that the integral of f of x dx will be the integral of 5x cubed dx. And this will be, we will take out the constant, we apply the constant rule, so this will be 5 times the integral of x cubed dx. And now we apply the, so here we apply the constant rule, let's say. And now we will apply the power rule, so this will be 5 times, and let's be careful here, x to the fourth plus 4 plus a constant, so this would be 5 over 4 x to the fourth plus c. Again, c is constant. The fifth one, now let's just say we have a function, a polynomial function, which looks like this, x to the fifth minus 3x squared minus 7. All right, and now we will have that the integral of f of x dx is nothing else than just the integral of x to the fifth minus 3x squared minus 7 dx. And this would be the integral using now the linearity of the integral. Let me put it here. So linearity of the integral. So once we use this, this would be the integral of x to the fifth dx minus the integral of 3x squared dx minus the integral of 7 dx. And this would be equal to, let's write it again, and we'll take the constants out, minus 7, the integral dx. Okay, and now it's quite clear. So we will have the first one will be x to the 6 over 6 minus 3 times x cubed over 3 minus 7, which will give us x to the 6 over 6 minus x cubed minus 7. Right? Sorry, minus 7x here. Minus 7x plus c. Again, c is constant. Okay. Right? Because the integral of dx, who is the integral of 1 times dx, and the antiderivative of 1 is x, right? That's easy. Now, another example, if we take, let's say, f of x to be, let's involve some radicals here, 5 square root of x plus 4 sine of x. And again, we would like to compute the derivative, the integral of this. So the integral of f of x dx will be nothing else than the integral of 5 square root of x plus 4 sine of x dx. And this guy now, we're going to use the sum rule. And this will be the integral of 5 square root of x dx plus the integral of 4 sine of x dx. And this would be equal to, we're going to take the constant out, so this would be 5 the integral of square root of x dx plus 4 the integral of sine of x dx. So this would be, let's just say, so you see, we can write this in the following way. The integral of x to the power 1/2 dx plus 4 times the integral of sine of x dx, which will be equal to 5 times the, so this would be x to the power 1/2 plus 1 over 1/2 plus 1 plus 4 times, so minus, so it will be negative cosine of x, right? Plus c, and if we want to write this a bit, so this will give us 3, so it will be 10 over 3 times x to the 3/2 minus 4 cosine of x plus constant. Again, c is constant, is an arbitrary constant. And that's it. This is how you compute the integral, right? All right. Now let's see some other applications. So let's see applications of the antiderivative. And let's see the first example that I have in mind. So example is the following. Let's just say that the graph of a function, capital F, has slope. So the slope is 4x cubed minus x cubed minus 5, right? At each point, x comma y, and contains the point 1 and 2, 1, 2, and contains the point 1 comma 2. And now we would like to find the function f. Find the function f. Okay. All right. Let's look at it. So we know that since f has slope 4x cubed minus 5, right? Since we know that this is the slope, then this means that it follows that f prime of x is 4x cubed minus 5. So we know this, right? But we also know that the integral of f prime of x dx is f of x, right? So the antiderivative of the derivative is the function itself. So it will follow that the integral of 4x cubed minus 5 dx. So by applying the linearity rule, this would be the integral 4x cubed dx minus the integral of 5 dx, and this would be 4 times the integral of x cubed dx minus 5 the integral of dx. So this would be equal to, this will be equal to, so 4 times x to the 4th over 4 minus 5 times x, right? So we apply the power rule. So here we apply the linearity rule. Linearity and constant rule. So both of them. And this would be nothing else than just x to the fourth minus 5x plus c, where c is a constant. Right? So this implies that the graph of f of x contains the point 1, 2. So this means that 2 is 1 to the power 4 minus 5 times 1 plus c. And from here, which implies that c is 6. And finally, this implies that f of x is nothing else than just x to the fourth minus 5x plus 6. And that's the function we're looking for, right? We almost determined the function if you look here. The only thing we didn't know it was the constant c, but now we determined the constant c. So, all right. Now let's see another application, even more, I would say. So the second application. So let's say this is example 1, example 2. And this is more like physics. And it says the following: a particle moves along a coordinate axis okay, in such a way, that its acceleration right is modeled by, let's just say a of t. So this will be the acceleration. A of t will be 2 times t to the power negative 2 for time t greater strictly positive. So the time will always be positive. All right. Now, if the particle is at s equals 5. Wait, let me think. Okay, at s equals 5, when t equals 1, right? And has the velocity let's say v equals -3 at this time. Where is, so we're asked, where is it when t equals 4? So that is the question we need to, where is it at t equals 4? All right, let's translate everything. So, Okay, so now let's just say we have that a of t is 2 t to the power -2. And let me draw the following picture so that it will become clear. So you see we have the position here, as you know, s of t, right? And once you you can go to the velocity here, and we go back. So s of t, so here ds over dt will be v of t, right? And s of t will be nothing else than just the integral of v of t dt. But also, if we want to go to the velocity and acceleration from v of t to a of t, so we will go here to, so this is the derivative with respect to t, and we can say that v of t will be nothing else than just the integral. In fact, let me write it here. So v of t will be nothing else than just the integral of a of t dt. So you always have to have in mind this picture. So keep this picture in mind. So the velocity is the derivative of the position, and well, the position is the antiderivative of the velocity, as you can see it there. And the same story goes for the velocity and the acceleration. So the acceleration is the derivative of the velocity, or you can say it's the second derivative of the position, or you can say that the velocity is the antiderivative of the acceleration. All right, that's great. So we're given a of t, right? And now at t equals 1, we have that, and we said here that s equals 5, so s of t is 5. So we know it's right. So v of t evaluated at t equals 1 will be nothing else than, we know that this is -3. So we know this, as you can see, right, in the statement of the problem. Well, this means that what? This means that the acceleration, which is the derivative of the velocity, so it's dv over dt, will be -2t squared. Sorry, to the negative, wait, what is 2? Sorry. So this is 2t to the -2. Okay. Now, clearly, v of t, which we said that is the antiderivative of the acceleration, will be nothing else than the integral of a of t dt, which will be nothing else than the definite integral of 2 to the power -2 dt. And this guy here, if you compute this, and I'll leave this to you, the details to you as an exercise here, well, you can fill in blanks. This will be nothing else than 2, in fact, is okay, so it's -2 over t. -2 over t plus constant, right? And let's just say it's C1 here, because we're going to deal with a lot of constants where C1 is constant. All right, beautiful. Now, we know that, so what do we know? We know that v of t evaluated at t equals 1 is -3. So it follows that -2 over t plus c1 evaluated at t equals 1 will be -3. And this will give us that the constant will, we can determine the constant, right? C1 will give us, let's see, so -2, -3, so this will be -1. Okay, so the constant is -1. That's great. So this will give us that v of t, so the velocity function is -2 over t minus 1, right? So that's what we obtain, right? All right, that's great. But we know that, let's go see what do we, so at this time, where is it? Okay, so we're interested in the position. So at this point, we know the velocity. This is important. But now, we know that v of t is nothing else than the derivative, so it's ds over dt. So it follows that s of t will be nothing else than the antiderivative of v, which is the integral of v of t dt, and this will give us the integral of negative 2 over t minus 1 dt, right? Which will give us, if we take the negative sign, so this will be negative the integral of 2 over t plus 1 dt, and this will be negative the integral of 2 over t dt plus the integral of 1 dt, or it will be negative 2 times the integral of 1 over t dt plus the integral of 1 dt. All right, so this would be equal to, well, this will be, okay, let me write it like this. So it will be negative 2 times the integral of 1 over t dt minus 1 times the integral of dt. And this will be negative 2 times ln of absolute value of t minus t plus another constant, let's say c2, where c2 is a constant. Okay, that's great. And now we would like to determine this constant. So we'd like to see who this constant is. So now we know that, so let's see, what do we know? We know that s of 1 equals 5, right? So, if we plug it in, we will obtain that negative 2 times ln of 1, an absolute value of 1 minus 1 plus c2 equals 5. So c2 here will give us a 6. Okay, great. And now finally, we found the position function. We have that s of t will be nothing else than just negative 2 ln of absolute value of t minus t plus 6. And now if we go back to the problem, we need to find, look, let's go back. You see here, we need to find the position at t equals 4. So we have to evaluate s of t at t equals 4. So this will give us that, and thus s of 4 is nothing else than just negative 2 ln of 4 in absolute value minus 4 plus 6. And this will be 2 times 1 minus ln of 4 in absolute value. And anyway, you can play around with this if you want, but that's not the purpose of this problem. So that's the end of it. Anyway, that was a very beautiful problem, more a physics problem, applications in physical sciences of the integrals. And now I would like to draw your attention with one more thing. And after this, I think I'm gonna stop. And there's one last thing that I would like to draw your attention is we would like to see the geometric interpretation of the antiderivative. So we'd like to see the area as an antiderivative. And here, well, you will see that this integral, if we define the integral on a given interval, on a finite interval, let's say a, b, you will see that this is nothing else than just the area under the graph of f. So let's look at it. So we have, let's just, let me directly say that we have the following theorem. And this theorem will concern the, just like I said, the area as an antiderivative. The theorem says the following. So if I have a function, so if f is a continuous function, such that f of x is non-negative for all x on the closed interval AB, then the area bounded by the curve y equals f of x, the x-axis and the vertical lines x equals, let's say, a, x equals t, viewed as a function of t, viewed as a function of t, right, is an antiderivative so it's antiderivative of f of t on the interval AB. So that's what we need to know. So let's draw a picture so that we can see things clearly. And let's just say that the function goes like this. So this is the graph of f, so it goes like this and like this. And let's just say that we have it here, right? And this is A and B. Right, so okay, so this is the graph. This is the area, sorry. So this is what we will call, okay, I'm gonna write it here. So this is the area A of t, which will be nothing else than the integral of f of t dt on the interval AB, and you will see that we will write this area in a certain way. And this is the graph of, so this is y equals f of x, right? And let's just say that this we have this guy t here from A to B. Let's just say it's somewhere here. So you see it's mobile. You can it goes from anywhere between A and B, right? And in fact, maybe I should have just mentioned that A of t is without this area here. So let me just I think this picture will be more accurate. So this will be without this guy here. Right? So that will be the area. And you see there is something that's a missing part from T to B. Okay. And here, from here to here, that's important to know is that This is the interval AB. We will see that we'll define the so-called definite integral of f, and we will compute the integral from a to b. We will compute actually the area under the graph of f from a to b. So we'll also have this hole here. So this missing part from t to b. Anyway, now let me give you an example. So the example that I have in mind is the following. So we want to find the area under the parabola y equals x squared over x-axis on the interval 0, 1. Okay, so let's see this example. I would like you to keep in mind this picture, right? So now let's just draw the picture so that you can see. Okay, but first, let me just say that the area under the curve y equals x squared on 0, 1 is the antiderivative of f of t equals t squared on the interval 0, 1. So a of t is the integral of t squared dt, which is, you can compute it by using the power rule, so it's t cubed over 3 plus c, where c is an arbitrary constant. And now let me draw a picture so that you can see it better. So let me just say the arc of the parabola was like this. Here is 0, and let's just say that here is a t, and here it's 1. Right, so we're interested in this guy here. So as you can see, we know that a of 0 is 0, and thus it implies that t cubed, so we know that a of t is t cubed plus the constant, so t cubed over 3 plus c is, okay, sorry, we evaluated at t equals 0 is c, which is 0. Okay, so therefore we can infer that a of t is nothing else than just t cubed over 3. So now we're interested, what is the area? So we're asked, you see, find the area under the parabola y equals x squared over the x-axis on the interval 0, 1. This is very important. So this is, we're not done yet because I'm interested on the interval 0, 1. So now what I need to do is the following. So the area right, under the curve on the interval 0, 1 right, is a of t evaluate at t equals 1, which is, if you plug it in, is nothing else than just 1/3. And we're done. And that's the problem. Right? All right. I think I'm going to stop here. Well, this is just the first part of chapter 5. So in this chapter, we talked about the antiderivative. We saw how to compute integrals of various functions, well, elementary functions. Well, in the next lecture, I will talk about something new, what we will call the area as the limit of a sum, and that sum will be what we call the Riemann sum. And this will be very important because the Riemann sums, as we will define also the definite integrals. So I think now it's a good place for me to stop. Thank you very much.